Okay, good morning, everyone. Welcome to the morning session with three talks. First talk by Professor Charles Kane on fractional excitonic insulator. Please go ahead.
Okay, thank you. Good morning, everyone. And it's really, I'm really happy to be here. So thank you, Fan, and thank you, Allan, for having me. Though I have to say, so Allan, I don't have any mentoring relationship with Allan. I never worked for him, and I don't think I ever wrote any papers with him either. But for me, Allan has played a big role for me in my career as a role model, role model of what the right way to do physics is. And so he's influenced me a lot. So I first met Allan when I was a 25-year-old graduate student. You may not remember this. It was the first conference that I ever went to give a talk. And so it was a conference outside of Minneapolis in the fall of 1988. You remember the conference? Now you probably don't remember me from that conference. I'm not sure I was memorable at that time, but you made a big impression on me. So what I remember from that conference is, between the talks, people are always talking in the hallway. And I remember Allan, there's a crowd of people around Allan. And Allan was describing the way that he was thinking about edge states and the fractional quantum Hall effect. And I didn't know very much at the time, so I didn't really understand what he was saying. But I did know enough to realize that what he was saying was really interesting and sounded really important. So that was one of my motivations for going back and starting to learn about the quantum Hall effect. So, and then several years later, I did learn a little bit about the quantum Hall effect and thought about edge states, and so Allan's work on that was one of the first things that I learned about. And going forward, actually, when I started learning about the quantum Hall effect, also is this this beautiful paper by Steve and Allan, which sort of showed the way to think about the quantum Hall effect as a macroscopic phase of matter. And so that really sort of provided a direction for my career after I graduated from graduate school. And going forward, of course, there's this whole body of work that I associate with Allan about interlayer coherence. In the quantum Hall effect, which started off with quantum Hall ferromagnetism, and then excitonic coherence in bilayers in gallium arsenide and also in graphene. And one of the things that I really admire about Allan is that he does this physics which is really deep and beautiful and important, but in doing so, he has his feet so firmly planted on the ground in terms of what is really relevant to and practical for experiments in the real world. That's something I always admire and is a sort of a role model for me. I don't feel like I'm ever really able to live up to that, but it's something I always wish I could do. So later on, I was, of course, very strongly influenced by Allan's work on the spin Hall effect. And so in the summer of 2004, I was getting kind of bored with what I was working on. I was trying to find something new. And so one of the papers I stumbled on was this paper about the intrinsic spin Hall effect. So that struck me as something that seemed really fundamental and interesting and new. And so there were all these things swimming around. I was also, these were the days when graphene was just coming on. I was thinking about that too, and it all sort of got munched together in my head. And I noticed some connection, wrote a couple of papers, and I wasn't quite sure what I had. And so I remember I met Allan again at a conference in Lyon in the spring of 2005. This was the first time that I ever gave a talk at a conference about the quantum spin Hall effect. So I had just finished a paper where I introduced a Z2 topological invariant to describe the quantum spin Hall effect. And I thought what I had was kind of interesting, but I wasn't so sure because it was about graphene, and everyone knows that the spin orbit interaction in graphene is puny, and so I wasn't sure that it was going to be very interesting. But I met Allan at this talk, and Allan was very encouraging to me. And so that meant a lot to me at that time. So thank you, Allan. A year later, I met Allan again in Würzburg. This may have been the same conference where you had the memorable lunch with Adi and Jim. I'm not sure if it was the same conference, but in any case, at that conference, that was the first conference where I learned about mercury telluride. So this was just before the BHZ paper came out, and there was some preliminary talk about that. And at that time, I didn't know anything about narrow gap semiconductors, but I had these wonderful conversations with Allan because Allan did know about this stuff, and Allan knew that this was something that was going to be important. And so then I remember going home and then starting to learn about narrow gap semiconductors, and that was another important milestone for me. So throughout my career, I've always looked up to Allan, and so my talk today is going to be a little bit more less feet on the ground, but it is inspired by some of these works. So you will see some of these things kind of showing up again in a little bit of a different way. So what I want to talk about is an idea that I had for what I'd like to call a fractional excitonic insulator, which is basically a strongly correlated fluid of electrons and holes that is kind of like a fractional quantum Hall state. Okay. So this is a work that I did a couple of years ago. And then I got distracted by something else. And then in the last 6 months or so, I've sort of picked it up again, and with a new student, Stephen Gassner, and also I've been talking with Adi Stern as well. And I'd like to introduce this idea of higher angular momentum band inversion. And I had hoped that I would be able to erase the question mark on this slide, but we're not quite there yet. So at this point, maybe this is still a questionable route to a fractional excitronic insulator, but maybe it's something that's still worth thinking about. Okay, so we all know about the quantum Hall effect, okay? The integer quantum Hall effect occurs with filled Landau levels, but of course, you don't need a magnetic field. You could have an energy band that has a Chern number, okay? And so this is a nice thing. And one can ask the same question about the fractional quantized Hall effect. Of course, Laughlin showed us the way for thinking about the fractional quantum Hall effect in a fractionally filled Landau level. And one can ask the same question about whether that could arise without a magnetic field. And of course, there was early theoretical work that suggested that indeed this should be possible. And basically what we're trying to do when we're doing this is we're trying to make a flat band that you can partially fill, and that flat band has a Chern number. So basically, you're trying to make a Landau level without the magnetic field. Okay, and then if you fractionally fill it, then there was numerical evidence that you could get something that looked like the fractional quantum Hall effect. So this is a very important idea, and it's especially important these days in light of the recent experimental breakthroughs sort of making that idea come to life in the real world. And so there's been and especially in the twisted molybdenum MOTE2 and other materials, there have been observations of the fractional quantum Hall effect in transport, and also in looking at the basically the strata formula of the relationship between the density and the magnetic field. And so I don't really have anything to say about these experiments. They're beautiful experiments, but the point I want to raise here is that there's a sense in which they're kind of the same fractional quantum Hall effect that we had before, because they're arising in a situation where you have a fractionally filled band, where you have fractional filling. Okay, and I want to ask the question: is this an essential ingredient for achieving something like a fractional quantized Hall state? Okay, and I'd like to suggest that there's sort of an extreme opposite limit that one can contemplate. Okay, and that extreme opposite limit we sort of already know about in the context of the integer quantized Hall effect, and this is what I like to call the band inversion paradigm, which is that a way you can achieve a Chern insulator is to take two trivial bands and have them cross each other. Okay, and if they interact with each other in the correct way, you open up a gap and you get a Chern number. Okay, one can write down a very simple model for this, just a two-band model, where you have a Dirac Hamiltonian, and then with a mass term, and then a regularization that tells you which side is the topological side and which side is not the topological side. And the point I want to make about this is that this is not a property of a band. Okay, it's a property just of the states near the Fermi energy. Okay, so everything deep in the band is completely trivial. Okay, all that's happening, all the action is at the band inversion. Okay, and so a way we can think about this is we can think that, well, I want to think of my uninverted state as being like the vacuum. Okay, and then what we're doing is we're having electrons and holes in the vacuum. So let me talk about this same situation from the point of view of electrons and holes. Okay, and so the mathematical thing you can do is to just do a particle hole transformation on the valence band, and this is the same particle hole transformation that Allan, of course, thought deeply about in the context of bilayer excitonic condensates. Okay, and so if you do that, then this simple two-band model of a Chern insulator then turns into something that looks like a BCS superconductor. Okay, and in particular, the pairing term that will give you a Chern number is sort of like a P plus IP excitonic pairing. Okay, and so this is exactly the same two-band model, but now I can think of the ground state is going to be like a BCS wave function of the particle hole pairs. Okay, and it's sort of like a condensation of P plus IP excitons. Okay, and the signature of being in the topological phase is sort of what the wave function of the pairs looks like. There's a weak paired state and a strong paired state. This is exactly the same kind of analysis that Nick Reed introduced when he introduced the notion of a topological superconductor, P plus IP superconductor. Okay, and now so I'm calling this a P plus IP excitonic condensate, but I have to admit that this is a little bit of an abuse of terminology, because there's no spontaneously broken symmetry here. Okay, so for example, in Allan's bilayer quantum Hall, you can turn off the tunneling between the layers, and you can still get an excitonic condensate. Okay, here it's as if we still have the tunneling on. Okay, so the P plus IP pairing is a single particle term that's in the Hamiltonian. You don't need interactions in order to get this. Okay, but the ground state is like this condensation of excitons. So the question I want to ask is, can we? So this state is some state that's built out of just the electrons and holes, okay, which are excitations of the vacuum. And so I want to ask, can I contemplate more exotic states? And so what I'd like to propose is something I'll call a fractional version of this. And one way I can describe it is by describing a wave function for the electrons and holes. Okay, and so this is my way. So it's a sum over all numbers of electron hole pairs. Okay, and then I have a wave function for all of the electrons. The electrons are at Z and the holes are at W. And so this thing, it kind of looks like a Laughlin wave function. And I'd like to argue that there's a sense in which it is a Laughlin wave function, but it's a little bit different because first of all, the Laughlin wave function has a Gaussian piece, okay, which really is reflecting the magnetic field, okay? And the other thing is that this wave function has a denominator, okay? So it has Z's and W's in the denominator. So it's sort of like a Halperin bilayer wave function, but it has a denominator. And you might worry that this denominator is singular. It blows up when the electrons and holes are on top of each other. So I want to argue to you that this wave function, in fact, would describe a quantum Hall fluid. Okay, and importantly, it's a quantum Hall fluid where it's not tied, where the M here is not tied to a fractional filling of any band. Okay, but you might worry that this, how could this be right? So there is one situation where I know that this is right. Okay, and so let me tell you the situation where I know it's right. I know it's right when M is equal to 1. Okay, and M equals 1, of course, is the integer quantized Hall effect. And so let me show you that this wave function is, in fact, the exact ground state of this simple two-band model that I told you about. Okay, so it's exactly the two-band model at a particular sweet spot of the parameters. So in the two-band model, there are two parameters. There's the Dirac mass, and then there's the coefficient of the linear term. Okay, and I'm going to choose a particular ratio of these. And if you do that, you do the BCS theory. And when you do BCS, you have the energy is the square root of E squared plus delta squared. And so the magic thing that happens when you do that is that square root turns into the square root of a perfect square. Okay, and when you do that, when you calculate the pair wave function, you have to do VK divided by UK, and that turns into exactly 1 over KX plus IKY. And so that means the pair wave function is exactly 1 over Z. And so if I make my BCS wave function, the BCS wave function is going to be a sum over all numbers of pairs, but for each number of pairs, the wave function is basically going to be a Slater determinant of the pair wave functions. Okay, and so it's a determinant of 1 over Z minus W, and there's a wonderful theorem that says that the determinant of 1 over Z minus W can be written in this Jastrow form. Okay, and so this wave function actually really is the simple Chern insulator. Okay, even though now of course it's singular in the denominator, but that singularity of course is just hiding in the way I've regularized at this model at large K. Okay, so I want to say the singularity it's okay. All right, so I know this is right for the integer case. So now we can ask the question, well, is it right more generally? How do we think about that? And so how did Laughlin know that his wave function was a fractional quantum Hall state? Well, one of the ways that Laughlin was able to understand his wave function is with the analogy with the classical plasma. Okay, and so remember, so Laughlin said that if you look at the square of the Laughlin wave function, I can think of that as the partition function for a classical plasma. Okay, now of course, Laughlin's plasma has charges that are interacting with a Coulomb interaction, they're repelling each other, but they're in the presence of a neutralizing background charge. And this neutralizing background charge is because of the Gaussian term in the wave function, which is really because of the magnetic field. Okay, and so what Laughlin was able to deduce was that as long as m is not too large, then the Laughlin wave function describes a fluid. Okay, now if m is too big, the Laughlin wave function is not the Laughlin state anymore. The Laughlin wave function describes a crystal. Okay, but lucky for Laughlin, there was plenty of room in which Laughlin's wave function was a fluid, and that's what we have now. So with this new wave function, I can also think of it as the partition function of a plasma, but now it's a two-component plasma of positive and negative charges. Okay, and there's no neutralizing background. Okay, and so one can ask, does that describe a fluid? Okay, and so that question actually is the same question as the fate of the XY model. It's the same. It's precisely the Kosterlitz-Thouless problem. Okay, so we have a plasma of positive and negative charges interacting by a Coulomb interaction, and m tells you, characterizes the strength of that Coulomb interaction, and so this is exactly the Kosterlitz-Thouless. Okay, and perhaps as it had to for m equals 1, you're definitely in the unbound phase. So this really is a quantum Hall fluid. For m equals 3, you're on the other side of the Kosterlitz-Thouless. Okay, so if the fugacity is too low, then you'll go into a bound state, which is not going to be a quantum Hall fluid. Okay, so they're here. They'll be bound to each other. But if you allow yourself to imagine cranking up the density, then it's at least plausible that there could be a fluid phase even for m equals 3. Okay, so now of course this doesn't really give us guidance for how to convince the electrons to do this. Okay, and so I feel like I'm convinced that this wave function does indeed describe a fractional quantum Hall fluid that is not tied to the fractional band filling. Okay, what I'm less certain of is how to convince the electrons to do it. And so let me tell you one thought that we had about how to make this come about. And this is going to be an insight that where I'm going to draw on this old paper from Steve and Allan, thinking in terms of a composite boson theory. Okay, so one way you can think about the fractional quantized Hall effect is to think of it as a theory of bosons that are experiencing a transformed field. So you do a singular gauge transformation, attaching flux to the particles, and so then so what I'm going to do is I'm going to attach m quanta of flux to the electrons and minus m to the holes. Okay, and now of course in the magnetic field, this statistical flux cancels out the magnetic field. Okay, and so that makes this a sensible thing to do. Here, what's happening is that the statistical field of the electrons cancels the statistical field of the holes. So on the average, there's still no magnetic field. So these bosons, in principle, could condense. And so in mean field theory, there's no magnetic field, but of course the bosons will feel, the fluctuations in the bosons will feel the field, and so that leads to a Chern-Simons theory. Okay, and so one can write down a Chern-Simons theory for these two coupled Bose fluids, And what you see from that is they couple oppositely to the Chern-Simons field, and so there's a combination that couples, the charge couples, and this is really just the Chern-Simons theory of the fractional quantum Hall effect. But there's also the sort of relative phase between the two bosons, and that's not locked. Okay, and in fact, if the electrons and the holes are independently conserved, then this phase is precisely the Goldstone mode that you would have because of the spontaneous symmetry breaking in an excitonic condensate. Okay, so this gapless phase mode is something that so at this point it's not the same as a quantum Hall fluid because it has this gapless phase mode. Okay, and so the question is how do we dispense with this? And and how do we decide what M to use? I mean, here I just chose M. I could choose M to be whatever I want. Okay, I wasn't forced to choose M by what the filling factor was. Okay, to cancel out the magnetic field. Okay, so I can now return to this problem where I know the answer, which is nu equals 1, and ask how does nu equals 1 do it? And there, the upshot, I don't have time to explain the details of this, but the upshot is that for, there's a crucial role played by the excitonic pairing term, which has P plus IP symmetry. Okay, and so when you do this statistical gauge transformation, the term that, with P plus IP symmetry in terms of the fermions precisely turns into a sort of Josephson-like coupling between the two bosons and locks their phase, opening up a gap, turning it into a quantum Hall fluid. Okay, so this is the way that the problem that I know is right, works within this composite boson theory. Okay, and so what this suggests then is that maybe there's a route to making this happen for finite M, which is the same thing happens if I have P plus IP to the M excitonic pairing. Then if I do the transformation adding M fluxes, then this term then locks the phase and stabilizes this fractional excitonic insulator phase. Okay, and so what this suggests is a possible route to realizing this, which is to imagine that I invert two bands that differ in angular momentum by M. Okay, and of course I have to have strong interactions. Now you can ask, well, what happens? The simplest thing to think if you have this, if you don't have any interactions, then maybe this is actually even a little bit interesting in its own right. What would happen if you invert these two bands that differ in angular momentum by M is you get a Chern insulator with Chern number M. Okay, so what I'd like to suggest is that possibly with strong interactions, this sort of scenario could stabilize this fractional excitonic insulator. Okay, but this is something where we're often strong coupling. I don't have a theory I know is right to be able to convince you that this is true. So this is a target for doing some numerics, which is something we're trying to do right now, but we're not there yet. Okay, so I think it's 9:30 and I want to stay on time, so I think I'm going to skip. I think I'm going to skip this and just go straight to Allan. So thank you, Allan. I've loved listening to you over all the years. Thank you.
Hi, Professor Kane. Thank you for your wonderful talk. I have a question. Is there a generalization of the idea of ideal quantum geometry, etc., to the excitonic systems?
I mean, possibly. So yeah. So the real answer is I don't know.
Okay.
But so I mean, this is something I've been struggling with: is what are the ideal ingredients in order to make this come about? And so it's got to be some property of the bands, but also some property of the interactions. Okay, and so I'm not sure it's just the non-interacting bands that are necessary to think about. But I think that is definitely a very interesting direction to think about. You know, because certainly for the fractional churn insulators, there's a lot of sort of, I would say, I feel like it's sort of rules of thumb that have been developed that, you know, that for how to optimize a churn band to make it most amenable to the fractional quantized Hall effect. And so I think that's worth thinking about. Yeah.
Yes, maybe we can also think of it in terms of like hot and pseudo potentials with generalization to excitons, etc.
Yes. Yeah.
I can just ask. So we touched upon both the questions I had. One is that I still do not completely understand what to determine M. In the Laughlin case, it's very easy. It's just the filling, inverse of the filling. In this
Well,
case,
what I'm suggesting
yes.
is that M could be determined by the angular momentum of the bands that you're inverting.
But then it's just fixed because it has just one churn number. You are not going to see different fractional filling by changing any parameter
That's right.
of the experimental system.
Yes.
So it will be quite different in phenomenology.
Yes.
So that's
That's
good.
what I want. I
So
want
that's
it to
good.
be
No, I understand.
different.
No, I understand. Yeah. So we may not know exactly what M is. Let's say it's C, but the phenomenon will be so different, there'll be no question what it is. But my comment is that, as you know very well, Laughlin wrote down a beautiful wave function. It is incompressible, but that doesn't make it right. What makes it right is that energy is lower than
No, exactly. No,
and
and
that may not happen here.
it may not. It may not. That's why I still have a
So
question
that is
mark
the
on that.
big question.
Yeah,
I used to tell Bob that he should share his Nobel Prize with, Rezai and people like that who showed that it's a very good wave function.
Well,
right?
experiments.
No, the experiment did not prove, no, experiment did not prove his Laughlin wave function. Experiment only showed that there is an incompressible state. Well, one has to be very careful,
Fair.
This
fair
is
enough.
one subject where numerics actually was analytical tool, right? In some sense.
Yeah.
So that needs to be done here.
Well, yeah, and actually, maybe I'd like to talk to you because how to do the numerics is not, it's not as easy as doing it in the Lambda level. So yeah.
But that needs to be done.
I think we should.
Okay.
So let's say next speaker.
All right. Thank you.